In order to calculate forces exerted by moving fluids and to calculate other effects of flow, such as transport, we must be able to describe the dynamics of flow mathematically. To discuss the dynamics, we have to be able to describe the motion itself. The description of motion is called kinematics. We will be interested in the kinematics of continuous media, that is, in describing the motion of deformable stuff that fills a region. Specifically, we'll be interested in describing the displacement, velocity, and acceleration of material points in the two reference frames commonly used in fluid mechanics. We'll show how these two descriptions are related to one another. In addition to moving from place to place, an elementary piece of fluid is generally squeezed or stretched and rotated as it goes. We are going to focus our attention on the translation, not on the deformation. In this flow of water through a contraction, hydrogen bubbles have been used to identify pieces of fluid so that we can follow their motions. These pieces are quite large, however, and we would like to examine the motion of very small, infinitesimal bits of fluid. Therefore, it will be more convenient to have a computer simulate these motions and generate the visual displays for us. We will use open circles, as we are doing here, to identify material points. In elementary mechanics, we are accustomed to describing the position of a material point as a function of time, using a vector drawn from some arbitrary initial location to indicate the displacement. We will use open vectors, as here, to indicate velocity and displacement relating to material points, open points. In a given motion, we can compute the velocity and acceleration of such a point at each instant. Here we indicate the velocity by a vector attached to the point. In a continuous fluid, of course, we have an infinity of mass points, and we have to find some way of tagging them for identification. A convenient way, though not the only one, is to pick some arbitrary reference time, which we will call the initial time, and identify the material point by its location at that time. Mathematically, we would say that the velocity is a function of initial position and time. To accord with this description, we have shown the vector attached to the initial position. We could show the vector attached to the moving point, or use both. If we were displaying the motion of a group of points like this, whose vectors do not interfere with one another. To display the whole motion, and in more complicated situations, we avoid interference by showing the vector only at the initial location. To describe the whole motion, we would have to give the velocity of all the pieces of matter in the flow as a function of time and initial position, like this. This description, in terms of material points, is called a Lagrangian description of the flow. Such coordinates are called Lagrangian or sometimes material coordinates. From the Lagrangian velocity field, we can easily calculate the Lagrangian displacement and acceleration field. We can imagine attaching an instrument, like a pressure gauge, to a moving point to make what we might call a Lagrangian measurement. This sort of thing is attempted in the atmosphere with balloons of neutral buoyancy. If the balloon does indeed move faithfully with the air, it gives the Lagrangian displacement. Such Lagrangian measurements are actually very difficult, particularly in the laboratory. We usually prefer to make measurements at points fixed in laboratory coordinates. Classically, the idea of a field, such as an electric, magnetic, or temperature field, is defined by how the response of a test body or probe, like this anemometer, varies with time at each point in some coordinate system. Here we are probing in laboratory coordinates. We will always indicate such probing points, points in a coordinate system fixed in our laboratory, and the velocities measured there by solid points and solid arrows. Here is a grid of points fixed in space. We show the velocity at each point. A description like this, which gives the spatial velocity distribution seen by a probe in laboratory coordinates, is called an Eulerian description of the flow. Although the physical field is the same, the Eulerian and Lagrangian representations are not the same, because the velocity at a point in laboratory coordinates does not always refer to the same piece of matter. Different material points are continually streaming through the same laboratory point. The velocity that a fixed probe would see is the velocity of the material point that is passing through the laboratory point at that instant. It's an advantage of the laboratory coordinates that there's often a frame of reference in which the Eulerian field is steady.
Static pressure P is a force per unit area with dimensions of mass over length times time squared. The dynamic pressure, 1/2 rho v squared, has to have the same dimensions. Adding the hydrostatic head z doesn't work because it isn't dimensionally consistent. However, we can instead express the head as a pressure, rho gz, and now it is consistent. Of course, the Bernoulli constant, or total pressure, must have the same dimensions of mass over length times time squared as all the other terms. This basic requirement of dimensional homogeneity naturally leads to a set of non-dimensional parameters that describe all sorts of fluid phenomena. By understanding the role of these non-dimensional parameters, we can learn a lot about fluid phenomena without actually having to solve the equations of motion. There are a lot of these non-dimensional parameters, but the most important one in fluid mechanics, which comes directly from non-dimensionalizing the Navier-Stokes equation, is the Reynolds number. It's defined as the ratio of the inertial force to the viscous force on a body, and it's equal to rho VL over mu, or just VL over nu. When the Reynolds number is much less than 1, as in this bead falling through shampoo, the flow is dominated by viscous effects. We call this creeping flow. When it's much greater than 1, as in the case of this airplane, the flow is dominated by inertial effects. The Reynolds number is named for that great father of modern fluid mechanics, Osborne Reynolds. Another very important non-dimensional parameter is the Mach number, named for Austrian physicist Ernst Mach. It's defined as the ratio of the speed of a flow, v, to the speed of sound, c, and it determines a flow's compressibility. For example, cars usually travel at speeds less than 1/10 the speed of sound, where we ignore any small density changes and consider the flow to be incompressible. On the other hand, some flight vehicles break the so-called sound barrier and fly at supersonic speeds, or Mach number greater than 1. When the Mach number is around 1, as in this transonic wind tunnel test of a space shuttle model, small speed changes make a big difference in the flow pattern. This leads us to the powerful concept of similarity. We can test a scale model of a commercial jetliner in a wind tunnel, for example, and expect to get results similar to those of the full-scale aircraft, so long as we make sure that the Reynolds and Mach numbers of the model match those of actual flight. A lot of wind tunnel testing, and nowadays CFD as well, go into the design of a commercial jetliner.